Welcome to EDU World Space.
This is chapter 21, problem number 58. We have an electron moving to the right with the speed of 7.5 times 10 to the power of 5 meters per second, and it enters an electric field parallel to its to the direction. So let's say the electron is moving to the right. So we have the electric field parallel, but we don't know if it's towards right or left. But we know that if it started at a point A, let's say with this initial speed, when it reaches a point B being 4 centimeters away from point A, it stops. So its speed becomes 0, which means it's slowing down as it gets from A to B, right? So in part A, we're asked the direction of the electric field, right? The direction. So the first thing to remember, if as we're going A to B, the electron decelerates, right? Its speed drops to 0, which means there is a force acting in a direction that is opposing the direction of the speed, right? Slowing it down after traveling 4 centimeters. So this must be the direction of the electric force then, right? To the left. Now, since we know the direction of the force, how the direction of the electric field is related to it is Q times E, right? In our case, our Q is negative E, right? Because this is an electron. So it's negative E, capital E, which is the electric field. So if the left-hand side of this vector is to the left, then we have this negative sign and it flips and makes it to the right. Right? So the electric field is to the right, based on that logic. Now, in part B, we are asked the magnitude of this electric field. So we're literally asked the magnitude of this electric field, right? So again, we're going to use a kinematic equation because we know that after traveling 4 centimeters, well, the initial speed is what is given to us in the problem, but final is 0, and we know that the distance traveled in the x direction is 4 centimeters, right? So using our kinematic equation, that gives us the final speed in terms of the initial speed. So V final equals V initial, V final squared equals V initial squared. Since it's decelerating, right, it's negative 2a delta x. V final is 0, so the V initial squared equals to 2a delta x. So if we divide both sides by 2 delta x, we get the acceleration. So acceleration is V initial squared over 2 delta x. So if you calculate the acceleration, then it's 7.5 times 10 to the power of 5 meters per second squared over 2 times 0.04 meters. So then that would be equal to 7.03 times 10 to the power of 12 meters per second squared. Since now we know the acceleration, we know from Newton's second law, the mass of an electron times the acceleration gives us the net force acting on the charge, and in this case that equals to Q times E. That equals to the electric force, the Coulomb force acting on it, right? So if we divide both sides by the charge, since we're talking about the magnitudes, let's put the absolute value. So then if we cancel out the charges, we can get to the magnitude of the electric field as m of the electron times the acceleration of the electron divided by the absolute value of the charge of an electron. So m would be equal to 9.11 times 10 to the power of negative 31 kilograms, as you know, and as you can look it up on your textbook. The acceleration we found to be 7.03 times 10 to the power of 12 meters per second squared divided by 1.602 times 10 to the power of negative 19 coulombs, right? The magnitude. So then from here, what we get the magnitude of the electric field to be is 40 newtons per coulomb.